Hi everyone, welcome to introductory Python tutorials with a special focus on image processing. And I hope you have subscribed to this channel by now. If not, this would be a great time to do that. In the last tutorial, we started to understand some of the standard deep learning models that are out there, for example, like VGG16 and ResNet and Inception. And we also started to understand how they can be used towards transfer learning. For example, these models can be trained on ImageNet dataset with millions of images. And what does that mean? That means it already knows how different structures and shapes would look like. So if we can use that as a starting point for our applications, maybe our training can be a bit faster or even more accurate depending on how much data you have. So in this video, let's build on that discussion by looking at how we can use these pre-trained models as encoders in our unit. And for that, we are going to use a existing library called Segmentation Models, and that library has a couple of issues. I'll talk about that to fix those. It's easy, but it's so powerful. It's worth spending the time to fix any issues that show up while using that library. So let me put it, let's continue the discussion and then I'll talk about the issues later on. We looked in the last video, we looked at what VGG16 was, right? I mean, it's a convolutional layers up to a certain point, and then you add the dense layers to make it a classifier. In this example, it's designed to classify 1,000 different features or classes in the ImageNet database or dataset. And there are two variants of VGG, 16 and 19. And the next, ResNet, the key thing here is it adds skip connections. So it makes it, so it addresses the vanishing gradient problem where you keep adding more layers and make your model deeper. And the gradient actually gets multiplied as you backpropagate. And then it doesn't update at some point because the updated, delta, or the updated change is so small that it doesn't matter, right? So then your model is not training, it's not learning. So it addresses that. And Inception addresses the fact that you have features of different sizes, different ranges in your image, and how do you address that? So it actually includes a way of including, in this example, 1 by 1, 3 by 3, and 5 by 5 convolutions, so it learns at these different scales. So that's what Inception's key thing is. And finally, EfficientNet is by Google, and it is designed to optimally scale your convolutional model in all dimensions like depth, width, and resolution. And it has been proven to offer better accuracy and better throughput. Well, it's EfficientNet. So we can use any of these as backbones for our unit model. What do we mean by that? What do we mean by the backbone or as encoder? Well, you have a typical unit, right? I mean, this is what we programmed from scratch a couple of videos ago, where we took an image, this unit, and we defined convolutional block, encoder block, decoder block, and we put it everything together. Now what I'm proposing is, let's think about this as on the left hand side you have the encoder, right? On the right hand side you have the decoder. What if we replace the entire encoder? The entire encoder is without the skip connections, just the encoder is just a convolutional neural network that's going from some large image size to a small image size. Just a typical encoder. Yeah. In fact, without the skip connections, this is just an autoencoder. Again, we talked about this a few tutorials ago, how this unit is basically an autoencoder. When you add these skip connections, that makes it a unit appropriate for semantic segmentation. So just take the encoder, replace it with something else. That's what we are proposing right here. And why? Because we can benefit from transfer learning. Okay. And the decoder part, what do we do then? Then we can programmatically build this up, the decoder, because we know what the structure of encoder is. And we know that the decoder is symmetrically opposite to the encoder, where you're just upscaling or conv 2D transpose all the way up. And then we add the skip connection. So that can be programmatically built up. I mean, I'm not proposing that we do that in this tutorial. Someone else already did that, so we just benefit from that library. Now, I mentioned about segmentation models as a library. Why do I like it? Because they offer a few ways. You can use unit, like the one we have been talking. You can use LinkNet architecture. Read more about these. I should say I'm not a big fan of any of these other than unit. So that's the reason we are spending a lot of time talking about UNet. So any of these architectures can be used with VGG, ResNet, pick one that you like, EfficientNet, and so on. All of these are trained on ImageNet database. So they all come with ImageNet weights. So much to experiment with, right? I mean, if you really want to work with EfficientNet, go ahead and import something and then go ahead and see if that works very well for you. So anyway, this is a great library. That's why whatever the flaws it comes with, we should be able to fix it and still use these segmentation models. Now, what do I mean by the flaws? Well, if you define your TensorFlow to be less than 2.0, like 1.4 or any of those, then usually you don't see much of any issues. So if you're using Google Colab, you can define at the top that use TensorFlow 1.x. But I don't like to do that. I want to use the latest stuff. So with the latest stuff, meaning if you're using TensorFlow greater than 2.0, you will run into issues. And what issues am I talking about? So here is one of the, again, most of the errors are very similar. I'm just showing you one error. And the type of error will show up depending on what, what backbone you're trying to pick. I don't remember which backbone this is. This is probably ResNet backbone, where it's trying to, you see how we are trying to get encoder weights to be ImageNet, and Google Colab threw this error. It says, hey, for that ImageNet, it's looking at this location, Python 3.7, distribution packages, classification models, weights.py, this file. Within that file, at this specific line, weights path, right? Because we are saying bring these weights. At that weights path, it doesn't know what to do with this because there is no keras_utils get file. Okay, we need to fix this. We need to just go ahead and edit. You can do this in Colab. If you're working on Anaconda or your own local desktop, go ahead and find where your Python 3.7 is, distributed packages under Anaconda or whatever environment you're working under, and then find that weights.py file and edit it to reflect that in latest TensorFlow, this thing, keras_utils.get file, has been changed. So you can fix that by just adding this line from tensorflow.keras.utils import get file at the top, and then just get file here. If we run into that issue, you'll see how we are going to fix it. Okay, but I just want to make sure you're aware of this. Because I don't want to show something and then it doesn't work for you. Leave it in the comments if you run into any issues, and we'll see if if we can help you out. But again, like I said, I'll show one method in this video. Once we get onto the code, I cannot imagine all the scenarios that you'll be working at, but you know exactly how to fix these things once you see. Okay, let's jump into the code right now and design our UNet with the data that we already had before we worked with. So there are only a few things that you need to change. I'm going to share the code with you anyway. Okay, so first of all, segmentation models. If you Google search for that, segmentation models, you'll see a GitHub page that has a very nice documentation, a few examples, how to install. But again, this is all based on older, Keras and TensorFlow, unfortunately. So we will, again, I'll show you how to handle. So let's switch to our Colab and let's work with this, our multi-class semantic segmentation. We already worked on this. Right now, we are just changing that to pre-trained weights. That's it. So let's go down and step number 1. Let's go ahead and install segmentation models. If you go to their page, they clearly mention how to do that at some point, I think. Right there, pip install segmentation models. That is exactly what I'm trying to do right there. Yeah, go ahead and do that. And that's installing segmentation models on your virtual machine in Colab. And now let's go ahead and import segmentation models. Yeah, it should import fine without any issues. You see it's using Keras framework. And this is what changed in the backend, right? They're using the older Keras framework. Now we're working on the latest Keras. If I go ahead and import Keras, let's also do import TensorFlow. import Keras, import TensorFlow. Now let's do print. What do we do? I can't even see. Print. Okay, let's go ahead and do that, and also do the same. I should have done this before. Okay, so I'm using Keras 2.5 and TensorFlow version 2.5 apparently, in case you guys wonder what versions I'm using. Okay, so there you go. We install segmentation models, and then let's go ahead and import the standard libraries that we have done before, OS, glob, CV2, all this to read the files and everything. And now I'm resizing, defining my size X, size Y, number of classes, and let's for now let's do 50 images. I have already trained it on, I think, 500 images or something, but for now I want to show you the process, so I changed it to 50 images. And I hope you watched my video, earlier videos where we used this same process, but let me repeat this. We are trying to sort the file names and the mask names, file names for images and masks. So when we load them, they load in exactly the same way. So there is a match between your images and masks. Otherwise, you may see a mismatch between them. So let's go ahead and load the images and load the masks. This may take a minute, even though this is only 50 images, because it needs to copy files from your drive to the virtual machine. Okay, so now let's do the same with masks. Okay, and these are the things we have done before, so that's why I'm going a bit fast. So watch my previous videos. There's no point in talking about the same stuff over and over. So we have total 1600 images. We only loaded 50 images and masks, each of size 128 by 128. And my maximum pixel value is 255, which means we have to scale these images. And my labels in the mask are 1, 2, 3, 4, which means we have to change them to 0, 1, 2, 3. Yeah. We have to start at 0. That's exactly what I'm doing right here, encoding labels to 0, 1, 2, 3. There you go. I've done this in the last video. And now let's look at expand our dimensions so they are at the right dimension for our neural network. And let's go ahead and normalize the images. This, I think this is an optional step because we are going to pre-process the data using whatever the pre-processing method in the backbone we are going to use. If we are going to use ResNet or VGG16, we are going to use the pre-processing that was defined. Again, I talked about this in the last video, which we'll get to in a second again anyway. You can split the data into XTrain, XTest, YTrain, YTest. Again, we are not training anything, so 50 images is for demonstration purposes only. Now I'm converting that into categorical, my Y values, because this is a multi-class segmentation. We need to convert our 4 classes into categorical. Okay, finally, our YTrain categorical shape. We have 40 images in the training data set, each 128 by 128 by 4 because we have 4 classes. Now, let's go ahead and load our parameters. This is the normal steps, right? Now, here is, let me provide a little bit of explanation here. So I'm importing TensorFlow, number of classes 4, and my activation I am defining as softmax because when we define our model later on, we need to define what the activation is because it doesn't know whether we are doing 2 class or 4 class. So I'm doing 4 classes, which means we need softmax activation. Binary, sigmoid, right? Okay, next what I'm defining here is my learning rate and optimizer, and I'm going to use the Adam optimizer, so I'm defining the optimizer right there. Okay, so far we got optimizer. We need to define our loss function and we need to define our metrics to track. For loss function, again, you can use categorical cross entropy or whatever loss function, but segmentation models provides a whole bunch of loss functions. Like one of those is dice loss function. Again, let me go back. This is important. And the best way to learn is just go into this library and then click on losses right there. And look at what they have. They have something called Jacquard loss, which is very similar to intersection over union loss. They have dice loss and what else? Binary cross entropy and categorical focal loss. Focal loss is great. And binary focal loss and a few combinations. You can actually import binary focal dice loss, which is binary focal plus dice loss. And they have categorical cross entropy plus dice loss. You can mix and match these. So let's get back. What am I doing? Here, from that losses, I'm importing dice loss, and I'm also importing categorical focal loss. Why categorical? Because I'm dealing with a categorical, like 4-class problem. And then I'm defining my own total loss here, which is nothing but dice loss plus focal loss 1 times. If you want to add more weight to focal loss, you can just add 5 times or something, yeah? But this is the loss function that I'm going to track as the model is, that I'm trying to minimize as the model is training. And for metrics, what metrics are we going to track? Well, let's track intersection over union score, and also let's track F-score. Okay, these are all, again, part of segmentation model.metrics. Go ahead and look at what metrics actually mean and get a good understanding of what's going on over there. So far, we used accuracy as a metric. We have used categorical cross entropy until the last video, but I'm introducing a couple of new ones here. Again, I talked about focal loss in one of my previous videos, so you should know what focal loss is. Okay, so these are just reusable parameters. Now let's come down and define the actual model. Let's work with ResNet34 backbone. I mean, we can work with VGG and EfficientNet and everything. For in this example, in this video, I'm going to work with ResNet34. And how do we pre-process our input? It's basically segmentation models dot get preprocessing. Preprocessing from what? From our backbone, which is ResNet34. If this is VGG16, just type VGG16 here, and the appropriate preprocessing will be acquired from this line. And then we are going to apply that preprocessing to my xtrain and xtest, my x values basically, right? So now we are preprocessing. Here is where we are defining the model. How do we define the model? From segmentation models, get UNet. Again, go ahead and look at the documentation for segmentation models library right there. Yeah, I'm just using this example, sm.unet resnet34, and use encoder weights as ImageNet. Yeah, very similar. Okay, so my model is from segmentation models, get UNet with a backbone of resnet34, encoder weights equal to ImageNet, classes equal to number of classes, which is 4. We have already defined that up here. And activation is softmax. That's it. That's what that line does. And once you do that, go ahead and compile the model using the optimizer. In our case, we're using Atom. Loss function is our total loss that we defined here, which is dice plus focal loss. And metrics equal to metrics. We have defined our metrics as a list. We are tracking 2 metrics here. That's it. In fact, if you feel uncomfortable with that, you can also do this. Model.compile using Atom, categorical, and whatever metrics you want to track. We did that until last video. Let's print the summary. Let's do this. This is where I assume it throws an error because we are trying to load the encoder weights as ImageNet. There you go. It says exactly the same screen that I showed you earlier. Hey, in this file, I don't know what to do with this, keras utils get file. So to check that, let's go ahead and add a line of code right here and see from keras underscore utils import get file. Does it work? No. That means in this keras, I cannot do that. How about from tensorflow.keras.utils import get file. That is working, which means I need to change this to tensorflow.keras.utils. Yeah, that's exactly what we are trying to do. So let's delete this line and let's copy this. Where do we change it? Well, whenever you do pip install or any of these, it's actually saving all of this into your local virtual machine, right? So we have to edit that file in the virtual machine. Google Colab does a great job by providing the link. Click on the link. It shows you that page. That is editable. Go ahead and remove that. You can do tensorflow.keras.get file. Sometimes that may not work, so I'll just do that, and at the top of this file I'm going to add that. That's it, and save. My weights.py got saved. Now let's exit out of this. If I run this line one more time, I'll get the error again because I haven't restarted the runtime. So don't worry, go ahead and restart runtime. This is not going to slow anything down because when you do that, your session is still active, so it's not going to go down to scratch and then remove any progress that you made. You can confirm that right here. Run this. This should be fast. Run that. And let's go ahead and run all of these lines one more time right there. And this time when I run this, it should be pretty fast because the images are already there. It just needs to load them, the 50 images. Let's load that and let's run these lines. Run that. Mask. Oh, I went too fast. There you go. There you go. There you go. And this should work fine this time. Yeah, I was going very fast. That should work. That should work. That should work. Everything should work. Now, what we care about is, does the next line work, right? I mean, does this part work? Let's go ahead and run it. There you go. It's downloading our ImageNet weights and everything is working fine. For what it does, these little errors, we can fix them and still be able to use them. Okay, so now let's go down. And from TensorFlow, yeah, we have already done that. And now you can go ahead and train the model. Well, I have done that on 500 images, I believe, and then I saved it. So let's go ahead and continue from the loading the model part. Yeah, I already saved it by giving an appropriate name, 50 epochs. And I loaded the model. And now, by the way, we are done with the actual part of replacing our encoder with ResNet. This is it. Let's make sure you understand that part. We have done that. My model is right there with backbone, encoder weights. That's it. Once you have that, you have your model.summary. You train it like you normally do. So the entire essence of this video comes down to this part. That's it. Once you're done, everything else is pretty much the same. Let's go ahead and look at my intersection over union values for the images that I just loaded. These are just 10 images, right? In my test images, we loaded 50. Of those, 40 are for training and only 10 images for now. Okay, and then let's print out the mean IOU. Last time when I was working with many images, I got 91.1% mean IOU, 91.9%. Excellent intersection over union, given the type of challenge we are working with here. And again, we have 4 classes. Remember, the second class is always difficult in this example to classify. So we got 83% IOU, but for others, we got pretty good intersection over union. So let's go ahead and print a few random images. There you go. That is almost identical. Let's segment another image. Again, mask and prediction. This is only 50 epochs using 500 images. And it's doing an excellent job because it already had a good starting point. So I don't need 200 epochs or 300 epochs for it to converge. So this is the power of transfer learning, where you can take already gained knowledge and extend that and customize it for your specific application. Let's continue the discussion of this transfer learning in the context of segmentation again, and let's see if we can extract features. So far, what we have done is we took these encoders and replaced it with a different architecture. Now let's see if we can actually take VGG16 or ResNet and use it as a feature extractor like I showed you in the last video, but then take those features and train a random forest or train a gradient boosting and then segment images or classify images. So stay tuned for those videos. Again, I know you like these videos, so please go ahead and hit the like button down if you like these videos, and again, subscribe to this channel. Thank you.